The main goal of this project is to enhance the strength of aerogel by adding different nanoparticles. We first started off by making some aerogel with a 1% loading of silica oxide. We then performed a compression test on the finished aerogel. A compression test measures the amount of force required to displace a material a specific amount, which we then use to calculate a stress versus strain curve in Young's modulus. What we found from our data was that the silicon oxide didn't have an effect on the Young's modulus of the aerogel, but the silicon oxide aerogel seemed to perform better at higher strain rates. We wanted to make the aerogel even stronger, so we considered using graphene. Graphene is a two-dimensional honeycomb lattice nanostructure of carbon atoms. It's strong, it's heat conductive, and conducts electricity. Then why is it used in zero commercial products? It's because graphene has a low shear strength and is hard to disperse. So we went with aminated graphene, abbreviated AG, which was developed by the UTD chemistry department. Essentially, aminated graphene is when you add a functional group to graphene, which allows it to covalently bond to polymers, all while retaining its original properties. So we started making some graphene aerogel. We then performed another compression test and calculated stress-strain curves, this time on our aminated graphene samples. What we found was quite interesting. For starters, the stress versus strain data seemed to suggest that different particle loadings of graphene didn't affect the strength of the sample, as 1%, 1.5%, and 3% loadings had nearly identical stress-strain curves. Our second discovery kind of shocked us. The Young's modulus of the aminated graphene was 134, twice the Young's modulus of silicon oxide in pure aerogel. Our findings suggest that aminated graphene yields the strongest aerogel by far, as it doubles the Young's modulus and performs significantly better at higher strain rates than silica 1% in pure aerogel. In short, we have significantly enhanced the properties of PUA aerogel using graphene. These findings have big implications. These aerogels can become electrically conductive, have potential applications in electronics, and become electromagnetic radiation shields. Other potential applications include heat or sound insulation, vibration isolation, and shockwave absorption. These applications have all become more practical due to our experiments in improving the strength of aerogel. Thank you, STEMcast.
Thank you, STEMcast.
Fantastic work, guys. I find it really pleasant to work with you guys in this series of summer camp, and I hope you feel the same way. I hope you find it inspiring and entertainment to do research here in UT Dallas.